So first of all, what is a polynomial function? Well, a polynomial function has x to different powers, and those powers are positive whole numbers. Okay? You can have any numbers in front. And we talk about the degree. So if I take out my highlighter here, the degree of a polynomial function is the highest power. So the highest power here is an x to the 5. We would say it has a degree of 5. Okay? Once you find that degree of 5, so this is my highest power here, degree of 5, the number in front of that highest power is called the leading coefficient. And we have two kind of main patterns that we see in these graphs. We have graphs that are odd functions and graphs that are even functions. So if you have, and this is what our notes are going to be, let me just zoom here a little bit bigger for you guys. If you have an odd degree, so that's like an x cubed, an x to 5, x to the 7, x to the 1. Our first note that we're going to say is that the end behavior acts like a line. So if your leading coefficient is positive, think about y equals 3x plus 5. The leading coefficient would be a 3, and it's positive. Lines that have a positive slope look like this. X cubed graphs with a positive leading coefficient are going to start in the bottom left and end in the bottom right. If your leading coefficient of an x to the 5 graph is negative, well, lines with a negative slope go down. The end behavior of any odd function is going to act the same as a line. Because that's their first odd function is a line, and the end behavior for all odd functions is the same. If you have an even degree, the end behavior acts like a parabola. So if you had a parabola with 3x squared plus 5x plus 1, if that first number was positive, you learned when you graphed parabolas that it opened up. And that was your end behavior. If you had a parabola that was negative 2x squared, it would open down. And your end behavior looks like this. This will be true for x to the 4, x to the 6, x to the 8 graphs. Any even powered graph will be the same. So we're going to use this to look at the chart that comes up next. So they start with a line. If you have a positive leading coefficient, you have a positive slope. It starts in the bottom, positive slope ends in the top right-hand corner. Negative slope goes down. Obviously, a line is an odd degree, and we just wrote that all odd degrees act like lines, so it's pretty surprising that a line also acts like a line. And a parabola, which is the second one, if it's positive, it opens up. Here's our end behavior. If it's negative, it opens down. There's our end behavior. And now we're going to see that pattern happen also with x to the cubed, x to the 4, x to the 5. So here's our x cubed graph. The leading coefficient, so the number in front of the x cubed is a +1. So it starts down here just like a line and ends up here just like a line. So off to the side, I would see this is an x cubed. I would probably write a little straight line and say, I know I have to start in the bottom left-hand corner for this graph, and I know I have to end in the top right-hand corner. The next one is a negative x cubed, so I would draw a little line with a negative slope and say, I know that it has to start in the top left corner and it's going to end in the bottom right corner, because the end behavior acts the same as a line. And when I get to next to the foregraph, well, now they're going to act like parabolas. So I see next to the foregraph, I see that the leading coefficient is positive. I think of a parabola opening up. There's my end behavior, and sure enough, on this graph, it starts in the top left, does some funky stuff in the middle, but then ends in the top right. And here I think of a parabola going down. And sure enough, it starts bottom left and bottom right, with some interesting bends in the middle. So this is our start for learning how to graph. The first thing we're going to do is we're going to say, what kind of function is it? Odd or even? X to the 5. Odd function. Odd functions and behavior acts like lines. So if it's positive, it's got to start down here and up here. This one starts down there, ends up there. Here I have a negative x to the 5. I think of a line because it's odd. It's going to start up here, end down there. So that's step 1 in graphing. Knowing the end behavior of the graph can help us draw the graph. So they have it summarized in here, but I find that these summaries would be hard to memorize. It is much easier to just draw a little picture of a line and circle your end behavior. And for even ones, draw a little circle, little diagram of a parabola, and there's your end behavior. You can read the words and see if that makes sense to you afterwards, right? For this one right here, as x goes to negative infinity, so as the x goes to the left, the graph rises to the left. And as x goes to positive infinity, in other words, as x goes to the right, the graph rises to the right. But the little picture of the parabola and the little picture of the line is way quicker for your brain to see it. So that's why I really like to do that. Some other key definitions you can highlight here. We got local maximum points. These would both be considered local maximum points. Local minimum point. This would be considered a local minimum point. The reason we use local is because if I draw a circle, so I'm going to take the minimum, for example. I'm going to draw a circle around it. Would you agree that the 1 point is the minimum in that circle? Outside the circle, like this is further down. It's not the absolute minimum. Just like somebody in this class is the tallest in this class. They are not the tallest person in the world, but they are a local maximum in this classroom. So we have in graphs local minimums and local maximums become very important. They become extremely important next year in calculus. Okay? This year, we're still going to be forced to use technology to figure them out. Next year, we can figure them out really easily if we have calculus. Okay, so let's go to example 1. First of all, you want to graph x cubed minus 3x squared with what information you have right now. Can you see that it's an odd function? So being an odd function, I know that my end behavior is going to act like a line with a positive slope. So when I go to graph, I know that it's going to be starting down here somewhere ending up there. I just don't know what's happening in the middle. Okay. Now we're going to learn, obviously, more advanced strategies to make the middle more and more accurate. Next year in calculus, it's going to be even easier to graph this more accurate. But right now, the only thing you've learned is about the end behavior. To graph the rest of it, the best you could do is just find some points. I love plugging in 0 as my first point because it's usually the easiest mental math. It's 0. So now I know it has that point. Could I draw a super accurate graph? No, I only have one point. Can you see that the more points you do, the more accurate your graph would get? Like, if I quickly did 1, 2, and 3. Well, 1 would be -2. 2 would be -4. 3 would be 0. Okay. So 1, I found out was at -2. 2 was at -4. And 3 was back at 0. Okay. I could plug in -1. -1 will be -4. So now I get some more points. I would guess that in between these points, it might look something like this. And if my end behavior has any kind of indication, this looks like it's a possibility. Now, yesterday I used graphing calculators. You could graph this on your graphing calculator. If you don't have a graphing calculator at home, you could use Desmos and see what it actually looks like. But a table of values gives you an idea, and the end behavior tells you where it should go. Because it's an x cubed, if I draw a horizontal line, the most I can go through it is 3 times. So I also know after these points that I've done, it can't loop back down and back up again, because then I'm going to get more points. So there's another little thing that can give us a hinter of what the graph is going to look like. Okay, I'm going to leave the x to the 4 one. All I'm going to do is say, I see that it's an x to the 4 is my biggest degrees of 4. The leading coefficient is negative. So I would know that's my end behavior. And I would just do a bunch of points to see if I could figure out what the rest of the graph looks like.
You don't want to do the points?
No, I don't feel like it.
Yeah.
You guys are ready for spring break. You want to go through things quicker. So this works out for you as well. I'm sure I have a video online somewhere that I did eat. But the table of values isn't rocket science. Right? You do as many points, but don't forget about a table of values. If you get a graphing question on your provincial exam and you're like, oh shoot, I forgot all of the super shortcut strategies. I'm stuck. No, you're not. You can always go back to a table of values. Sometimes I've seen students get 4 out of 4 on a super complicated transformation question because they forgot how to do it and just got table of values. And if you get 3 points that are right, and one of them is like the key starting point, you're going to get full marks. And you didn't even have a clue how to do a single transformation. That's wonderful, right? Math is not just about knowing always the best way. Sometimes it's about problem solving when we forget and knowing we have other strategies that can help us as well.